So today we are going to be talking about work and power. If you haven't done so already, please get your notes out and locate the sheet that says N4 work and power at the top of it. The first thing that we need to talk about is we need to talk about the definition of what power actually is. Power is defined as the rate at which work is being done, and it's usually measured in the unit of watts. And so you may have heard of watts before, but that's the new unit that we're going to be working with this unit. An example of power would be if you and your friend decided to grab a 50 kilogram box each and move them from the first floor to the second floor, which is a distance of 3 meters. Your friend happens to move the box in 5 seconds and you move yours in 3 seconds. So the scenario is that you guys are picking up a box, you're running up the stairs, you're faster than your friend. You've both done the same amount of work because you both went up the same height and moved the box and you moved the same box. However, you happen to have more power because you did it faster. And there's a formula associated with that. So we're going to talk about that next. The formula for power is equal to work divided by time, or P is equal to W over T. And so if we go back to those triangles that we did earlier this year, P, W, T, that's that triangle of fun that we talked about earlier, where if you cover up P, you can get work, or if you cover up P, you're solving for power, which is work divided by time. If you want to get work, you cover up work, the W, and you get power times time. And if you want to solve for time, you cover up the T and you get W over P. Some units to consider or think about. The power is always in the unit of watts. The work is always in the unit of joules, so that's coming back. And time is always in seconds. So here's an example of using the power equation. So a friend applies a 1,470 joules while lifting a box for a grand total of 5 seconds. So the question is, how much power do they use? Well, if we're going to use the formula, P is equal to W over T. When we substitute in the things that we know, P in this case will be equal to 1,470 joules over the time, which in this case is 5 seconds. So power, when you plug this in your calculator, power for this situation, 1,470 divided by 5 equals 294 watts. So that's one of the ways that we could use this formula. The next thing we need to talk about is this example problem where we have a forklift truck and it is picking up a 50 kilogram box that was initially on the ground, and it's picked up by an electric forklift. So the first thing that this problem is asking us to do is to draw an energy bar chart for the box. So in this case, we are going to be making the box our system. And if the box is resting on the ground, it doesn't really have any energy. So we're going to leave the first initial side blank. And the forklift is going to be actually doing something to the box. So it's going to be working on the box. So we're going to have our arrow here, cat. And so that's the forklift. Okay. And so the forklift puts in a very specific amount of energy to the system. And now the other thing that we have to keep track of is where the energy went. And the energy was then spent in this particular case in terms of gravity. So when we draw this bar chart, we're not going to worry about the electrical, even though that the forklift is electric, because the forklift isn't part of the system. So that's what our energy bar chart should look like. Now, if the forklift actually raises the 50 kilogram box 2 meters, how much work does the forklift do? Well, we have to first of all write our energy equation. And remember, our energy equation is the initial part of the system plus the final part of the system. So in this case here, initially we had no energy in the system because the box was sitting on the ground. We had some work being done on the system by the forklift, and then we had the box was fighting against gravity, so the energy in the system was gravitational energy. And now we need to remember way back to first semester where gravitational energy had a special formula, which was mass times gravity times height. So in this problem, we now need to substitute mass times gravity times height. So I have 0 plus W equals mass times gravity times height. So in this case, looking back at my problem, I see that the box is being lifted 2 meters, so that's my height. I see that the mass is 50 kilograms, and gravity has always been and will always be 9.8. So in order to solve this problem, I'm going to take W, which equals the mass, so that's 50 kilograms, times gravity, which is 9.8, times height, which is 2 meters. And so now, when I plug that into my calculator, 50 times 9.8 times 2, I get a value of 980 joules. Okay. Now, in the same problem, we have the same situation where initially there's nothing really going on energy-wise. The box is still the system. The forklift is still doing work on the box. And gravitational energy is still the energy that's present when the box moves. So question 3 says, if it takes 15 seconds to lift the 50 kilogram box 2 meters, how much power does the forklift require? So in this case, we're looking for power. And we know that power, according to our formula from before, was work divided by time. Now we have to remember back to the problem from just before where we decided that the work involved on the box was 980 joules. And the problem is telling us that the time is equal to 15 seconds. So I can plug those things into this formula. Power will equal work divided by time. So the work was from the previous problem, 980 joules, divided by the time, which was 15 seconds. So when I plug that into my formula, or into my calculator, 980 divided by 15, I get a value of 65.3 watts. Okay, so that's an example with power. Now, efficiency is the ratio of the useful power output to the power that was actually put in. So how much power we get out of the system versus how much power we put in. So it has to do with work and time as well. So whenever energy changes from chemical energy to kinetic energy, some energy is lost or dissipated. Efficiency tells us how much of that energy is not lost. That is, how much of that energy was actually used to do the task that we wanted it to do. So the formula for efficiency is power out divided by power in. And we have to be careful with percents versus decimals. We'll talk about that in a second. So in this particular example, if the forklift from just before uses 300 watts, that's our P in, of power, what is the efficiency? Well, in this problem, we are going to take efficiency is equal to power out divided by power in. Now, power out, we're told power in, we're told in this problem is 300 watts. The power in is coming from the forklift in the last problem, and the forklift in the last problem generated. Oh shoot! I put that in the wrong spot. Look at that. That's not okay. I gotta fix that. Oops! I should do the eraser. That's be better. So what we're looking at here, I put that in the wrong spot. Man, that's just silly. So I'm going to take my 300 watts and put it on the bottom. And the power out comes from the last problem, the problem where we calculated the fact that the forklift put in 65.3 watts of energy. And so when you do the math, you take 65.3 divided by 300, you get a value for the efficiency to be 0.22. Well, that doesn't really tell me much. So if I multiply that by 100 to get a percent, I get 22%. I get 22% efficient. And so that tells me a lot. So we put a lot of work in to get a little work out. So that's not very efficient. So your homework for the evening is to do worksheet number 4, work, power, and efficiency. There's 8 questions on it. It's a front side and a back side. And good luck.